SwayamPrabha. Digital India. Educated India.
Okay, good morning again, and we will start our lecture on characterization techniques on CCA alloys as well as high entropy alloys. What I will do in this lectures, I will demonstrate some of the case studies. We will start with some case studies which involve different characterization techniques like X-ray diffraction, EBSD and HRTEM, STEM and EDS, strain mapping, etc. If the time permits, we will concentrate on strain mapping, otherwise we will postpone it to the next lecture. So, when we talk about this characterization techniques, what are the things comes to the mind? Why are we discussing this for high entropy alloys? That is a question, right? So, we know the characterization techniques, most of them. Conventional techniques we know, like what are the conventional techniques we use for any material characterization? Any idea? Yeah. Yeah. So we start with X-ray diffraction for crystallographic identification or phase identification, optical microscopy for overall microstructures at very low magnification. And then you do some SEM and EDS for topography, secondary electron image or backscattered image, or you use phase specific diffraction techniques like EBSD. These are all phase specific diffraction techniques. Then what is that we have to think about when it comes to characterization of high entropy alloys? That is a question first I want to pose before I discuss anything. All these things we know, all these characterization techniques we know. And the interesting point is most of these compositionally complex alloys or high entropy alloys, they form a simple phases like FCC, BCC and HCP. As long as they form a simple phases, and these characterization techniques also will be useful. But where the question comes, the difficulty is when you have a multi-principal alloys, when it forms a microstructure, the lattice are quite strained because of different substitutional alloying elements, right? So when you have the lattice has some significant strain, then identifying the short range order or long range order or something like, suppose if you just think about the atomic scattering factor of all the elements, right? See, when we look at the X-ray diffraction techniques, the structure factor is something which we always calculate, right? So when you have a multiple principal alloying elements, and then if you consider the scattering factor of all these elements, and if they come very close, then there is a problem, right? So we will not be able to identify the elemental distribution or the short range order which comes out of this kind of. You should have a significant difference in atomic scattering factor by the elements, then your characterization techniques can identify them. Okay, so that is where we need techniques like neutron scattering or synchrotron scattering, synchrotron diffraction, neutron diffraction techniques, where you will have all these elements will have a very sensitive diffraction response. Then you will be able to distinguish between all these 3D transition elements, though they are closely related in atomic number. They have a very close atomic number in range. So that is about the diffraction part. Then apart from this XRD, we also use electron microscopy techniques. in electron microscopy techniques, typically we are interested in phase identification and then the diffraction information, selected area diffraction information, and then we try to correlate with the crystallography in a very localized region. And then if you want really an atomic scale identification, then we need a sophisticated tool like high resolution TEM. And then we have today, high angle annular dark field in STEM techniques, that is scanning transmission electron microscopy techniques we have. And we have something called atom probe tomography techniques, where you can just trace the atom by atom and then look at the morphology in 3 dimensions and so on. So the complementary techniques of all these sophisticated techniques will give us much more overview of these complex alloys. Then the idea is, when you look at all these techniques, it is not that you perform a characterization techniques for the whatever the equipment available with you. That is not the point. The point is intelligently choose which combination of the techniques will shed the light on the complex issues which you do not get from the conventional techniques. So that is the idea. Okay, so in view of that kind of introduction, so let me start that. Okay, so let us start with the microstructural features of aluminum, cobalt, chromium, copper, iron, nickel system. It is quite popular high entropy alloy systems, and then you just vary the aluminum content, then it evolves from FCC to FCC plus BCC mixture, and then at higher aluminum content it exhibits a BCC structure. This I think we have seen in the previous lecture also. So when you have these kind of multiple principal alloying elements, how do we understand the microstructural features? So we will integrate all these techniques, SEM, TEM, and selected area electron diffraction, energy dispersive spectroscopy, and X-ray diffraction, and then see how best we can understand this system. So all of us know that XRD is a very powerful technique in identifying the phases, especially the crystal systems. So this is an XRD pattern of this particular alloy as a function of increasing aluminum content. I would like you to look at these patterns and let me know, because this is very elementary. So you must have already seen this several times. So what are the phase selection, selection rule for identifying this BCC, FCC, and so on. So this patterns are indexed to FCC, open triangles, and BCC, solid diamonds, and then ordered peaks of B2 phase. So where is ordered phase? This is 1, 0, 0 ordered phase, right? That is a B2 phase, which is a part of this microstructures, right? So I think you should recollect this selection rule for particular FCC and BCC, and then if it is an ordered phase, what is the selection rule? So you should know that, and then you can identify this by this conventional XRD, and then we will come back to this when we go to the other techniques. So suppose if you look at the crystal system, how this multiple principal elements are forming a disordered BCC solid solution. If it is a random mixing, then it forms a disordered BCC solid solution. If it forms an ordered BCC like a B2 structure, then it is the crystal structure is like this. Okay. So the center of the B2 ordered unit cell represents a site that is preferentially occupied by aluminum, for example. note that there are several different mixing scenarios that could lead to B2 ordered structures. So, this also you should know. There are different possibilities by which you can form this in this particular alloy. And now we look at the microstructure again as a function of aluminum content, how it varies. What you are seeing is an SEM secondary electron image of the as cast aluminum, cobalt, chromium, copper, iron, nickel alloys with the different aluminum contents. So, the A is 0 aluminum and B is 0.3 and again C 0.5, 0.8 and 1. And there are a lot of markings, annotations are there on the micrograph. DR stands for dendrite, ID stands for interdendrite, and SD stands for spinodal decomposition. So, you have dendritic FCC phase, and then you have interdendritic FCC phase which is rich in copper, and then this is 0 aluminum, and if you reach 0.3 aluminum, then you see the DR phase trying to become dominant, and then interdendritic phase is also becoming less. Okay. So, you can see that if you reach the 0.8 or so, you can see that the interdendritic region is having some kind of some features are visible, right? Some kind of mixture is visible, and when it crosses 1% of aluminum, then you see that it is a spinodal decomposition microstructures, and then you have very small interdendritic FCC plus BCC mixture here. So, what are this? So, you have dendrite, the copper segregation in a small volume fraction of the interdendrites. The EDS results showed that dendrites were composed of multiple principal elements, particularly for low aluminum contents. Okay. As the aluminum content increases to 1, the dendrites develop a spinodal microstructure. So, what is spinodal microstructure? Now you know very well, right? So, because of the compositional fluctuations, the microstructure decomposes to two-phase mixture, right? A fluctuation in the composition. So, this changes whatever we are seeing can be related to the XRD results what we have seen in the previous, such that alloy phases at low aluminum contents are FCC, which is a copper rich FCC phase in the interdendrites, and multi-principal element FCC phase in the dendrites, and a mixed phase FCC, BCC and B2 at high aluminum contents. So, which we are exactly relating this with XRD what we are seeing. It is exactly matching with what we have seen, right. So, as the aluminum contents goes up, you start seeing a mixture of FCC plus BCC, and then beyond 1% you see the spinodal decomposition. So, this is some simple analysis. So, let us look at this, the spinodal microstructure or the alloy with 1% of aluminum. How does it look like at higher magnification, especially under transmission electron microscopy? What you are seeing here is a bright field electron micrograph, and then you have an inset selected area diffraction, and you have here B is a dark field image corresponding to 1010 superlattice spot of the SAD pattern shown in A. So, what you have is a composite pattern. It is not all of them are not a fundamental reflection. So, you have a fundamental reflection which shows as a square here. They are all fundamental reflection, that is 001 type zone axis, and then in between you see center, you see the superlattice reflection. So, you form a dark field image by one of this superlattice reflection, then you get this kind of an image. So that means whatever is appearing bright belong to that ordered structure. That's what it means, right? Because you are choosing the superlattice reflection. So whatever you appear bright here is corresponding to that superlattice microstructure. That's what it means, right? So let us look at other regions, like you have the TEM microstructure of dendrites of as-cast alloy is shown here again. In the C, you have different features. What are the features you are seeing? You have some precipitates and the corresponding selected area electron diffraction is shown here, and which is close to the FCC zone axis, and the dark field image corresponding to the circled spot of the SAD. So the dark field is produced by this diffracted spot, and then you see that lot of features inside this small domains, white domains are appearing, okay. And then if you zoom this white domain area, then you see that a layered structure, okay. You have one layer here, another layer here, another layer here. So alpha, beta, you can see that layer by layer you can see. So if you look at carefully, then again as I told you, you have these fundamental reflections pertaining to 001 zone axis, and then you have a superlattice reflections are shown here. And what we learn from this are summarized here. You have an alpha interplate which is about 70 nanometer wide, disordered BCC phase, that is A2, of a lattice constant 2.89 angstrom. So all these parameters you can derive from this electron microscopy. I mean, that's the idea. You get feature dimension as well as the lattice constant. And beta is again the plate of 100 nanometer wide, which is ordered BCC phase, B2, I mean with a lattice constant of 2.89 angstrom. And then there is an epsilon marked here. You can see that there is an epsilon here. It's a nanoprecipitation in the plate, which is 7 to 5 nanometers diameter. So you look at the feature dimension, it is less than 10 nanometers. So getting this kind of information under normal SEM is not going to help much. So you need to have a complementary technique like TEM. So get this idea, which is again from the electron diffraction studies. It is close to FCC phase, and delta is a contrast in the interplate due to the surface roughness effect of the TEM foil. Okay, so what you are seeing is, of course, all these contrast mechanisms, what you are seeing is basically because of the diffraction contrast, right? Not the any other mechanisms. So what is the summary? So we have an equimolar aluminum, cobalt, chromium, copper, iron, nickel alloy, contains various nanoprecipitates, which was shown in the previous images C to E. And the SAD pattern analysis of this precipitates shows that it is an FCC structure. And in the dark field, based on one of the FCC reflections, nanoprecipitates of various sizes appear bright, indicating that they are similar FCC structures. Okay. And then you have a BCC, which is a B2 matrix, appears dark because it does not produce any significant scattering in the vicinity of FCC reflection. So you should know why this appears dark here as well as here, right? Of course, the enlarged view of this TEM image shows much more details about this spinodal microstructure and various nanoprecipitates. So this is a summary of this. So now we will go to the case study 2. So what we have now looked at in the first case study is we looked at XRD and SEM and then TEM, how to correlate all of them. They are all giving a correct information, but then depending upon the resolution requirements, you change the characterization techniques. Now we go to the case study 2, understanding the fracture resistance behavior of cobalt, chromium, iron, manganese, nickel alloy. This is another high entropy alloy using backscattered electron diffraction imaging and EBSD, EDX and stereo microscopy. So we will combine all these techniques to understand this fracture resistance behavior. The previous case study, we combined several microscopic techniques to understand the microstructural evolution in a as-cast material. Here is the very interesting alloy which is exhibiting extraordinary properties like very high fracture toughness. So fracture resistance behavior. How do we understand that? And what are the techniques we should use? You see, the characterization techniques used here and the previous case are quite different. This is what I said. So you have to choose the characterization techniques in such a way that you get an answer intelligently. You cannot randomly go and do all the characterization, right? So the XRD studies indicate that this alloy forms a single phase FCC solid solution, and the EDX verifies the nearly homogeneous cobalt, chromium, iron, manganese, nickel composition in a solid solution. The interesting property is this alloy exhibits excellent damage tolerance. What do you mean by that? What do you mean by excellent damage tolerance? No, damage tolerance, excellent damage tolerance. What do you mean? Yeah. So when you have a damage tolerance, it is simply represents the fracture toughness. Suppose if you have a defect in the material, so a crack is there in the material, but even with the presence of the crack, how much the material can sustain the load or sustain the life. So that is called damage tolerance. Right? It's a fracture mechanics term. Okay. Yeah. EDX, we have been using EDX. I think I did not mention that, but I did not show that. Okay. So mostly I was looking at only, I just mentioned the EDS results showed the dendrites were composed of. I did not show that spectrum here, but the primary focus was to compare the diffraction, X-ray diffraction, electron diffraction, SEM morphology and TEM morphology, phase evolution. Of course, EDS we have used. Yeah, I didn't show that. I didn't bring that spectrum. So the fracture toughness values exceeding 200 MPa square root meter. So 200 MPa square root meter fracture toughness is significantly high. Even if you talk about very high specialized steels, you talk about close to 100, 80 to 100. These are all considered to be very high fracture toughness materials. We are talking about 200 MPa square root meter. So where does this toughness come from? So you measure some mechanical behavior, but we need to understand why the material is like that. So that is where the characterization becomes so important. It's good that we are able to measure some special properties like fracture toughness, very expensive experimental technique, very expensive. Conducting fracture toughness is very expensive. That's good, we got a value, but then how do we understand this? That's why we need this kind of combination of sophisticated characterization techniques. And another interesting point is both strength and ductility increase at cryogenic temperatures. Okay. Contrary to the trend in the most alloys where ductility typically decreases as strength increases, right? That is the usual trend, right? But especially when it comes to the cryogenic temperatures, how this ductility is preserved. See, this is a puzzle, right? So we need to understand. So when this cobalt, chromium, iron, manganese, nickel was cooled from room temperature to 77 Kelvin, the ultimate tensile strength was found to increase by 70%, reaching 1280 MPa, while the tensile ductility increased by 25%, such that the true strain is more than 0.7. The nature of this interesting behavior in cobalt, chromium, iron, manganese was uncovered using microscopy to examine the sample regions surrounding the fracture toughness crack tip. So we are looking at very closely to the crack tip, how the crack grows, right? And we are not just looking the general characterization here. General characterization is anyway done, but our interest is to capture the why the fracture toughness is very high. So the complementary techniques, we are including stereo microscopy, SEM, EBSD, EDS and BAC imaging. Let us see what we see. Of course, there's some information about this alloy preparation. This cobalt, chromium, iron, manganese, nickel alloys were prepared by arc melting and drop casting into a rectangular cross section mold of this dimension. The specimens were further processed by cold forging, cross rolling, producing 60% reduction in thickness and annealing at 800 degree for 1 hour in the air. Annealing process produced a fully recrystallized equiaxial grains of 6 microns, which is shown in the BSc image in the next slide. And then you will also identify some chromium rich, manganese rich particles with the 2 micron in diameter size are dispersed throughout the solid solution matrix. So this is the background of this alloy. And this is the BSc image, backscattered electron image. So you should know what is backscattered electron image. What is backscattered electron image? Huh? It is sensitive to atomic number, and the heavier the atomic number, it will give a better contrast. Right? So that information you know at least. So you can see that these alloys showing about equiaxial, grains are recrystallized grains showing 6 microns containing several recrystallization twins. I don't know how many of you can identify twins here. Are you able to see the twins here? These are all twins. There is a twin here, there is a twin here, twin here. The insert on the top right shows the EDS results verifying the equimolar composition of the solid solution. So you have all the elements in the matrix, okay, chromium, manganese, iron, cobalt, nickel. And the insert on the middle right shows the simple X-ray diffraction pattern which corresponds to the FCC. This is a FCC matrix. And when we look at the fracture surface, the alloy exhibits the crack surfaces are covered with the ductile fracture dimples, and distinct particles are observed within these dimples, which were shown to be manganese rich, chromium rich using EDX. And these particles were identified as micro-void initiation sites. So wherever you have second phase particle dispersed in the matrix, that interface is vulnerable for creating a void. This is the message you should get. Okay. These micro-voids grow and coalesce when the sufficient tensile stress is applied, ultimately leading to the ductile fracture. And there is 3-dimensional fracture surface models were constructed from SEM stereo image pairs, which shows the distinct difference between fatigue pre-crack regions and final ductile fracture zone, where the dimples becomes most pronounced. I will explain all these 3 points one by one. So look at this interesting image. So this is the CT sample, compact tension sample, typically used for fracture toughness testing. And this is the pinhole. There is a pin inserted here, and then it is being pulled like this, and then you have a notch, and the notch after that there is a crack, pre-crack. It's called fatigue pre-crack. It is done by a fatigue loading, so naturally grown crack is measured to the predetermined length, and then finally you pull them. Once the natural crack is grown to the predetermined length, then you try to pull them and look at the load versus displacement curve. From there you calculate the toughness. Okay. So that is a part of a mechanical behavior course you would have studied. But here what is that we are interested? So you can look at this white square around the crack tip is zoomed here. One is liquid nitrogen temperature, another is room temperature. So we have two situations. That's what the sample is prepared. One is cooled to 77 Kelvin, another is cooled to room temperature. So you have two type of microstructure, and the crack tip shows a very interesting observation. You see a lot of micro voids are there close to the crack tip, and they will all coalesce like this, and then the crack propagation happens. And the same region is now marked by an EBSD map, and you can see that a small rectangle square here is being zoomed here into this EBSD map. You can see that, and we will look at this details one by one. And what you are seeing in the bottom is BSC image, and BSC image has been zoomed from this region. You can see that the zoomed region is shown here, and the corresponding the zoomed region EBSD is also shown here. So question to you is, what is that you see from this? So we are from this, all these features, we are going to deduce the deformation mechanisms near the crack tip under the plane strain condition. So when this section of the material, the specimen experiences a plane strain condition, right? That's why it's called a plane strain fracture toughness, right? K1C. And low magnification SEM images of the sample tested at room temperature and 77 Kelvin show the ductile fracture by micro-void coalescence. So this is a micro-void coalescence here both. EBSD images of room temperature sample show the grain misorientation due to dislocations, representing the dominant deformation mechanism. Annealing twins are also present as in the crack-free regions. So you have crack-free regions also having a big twins. They're all annealing twins. You look at the scale bar here, it is about 5 micron here. Then it's more than 10 micron length, right? This region. So at 77 Kelvin, you have nano twinning is seen on the BSC. So you have, you look at the scale bar, it's a 2 micron. And then you have this bar zoomed region, you can see this is just 1 micron. Okay, so you have nano twinning is seen in BSC and EBSD images. And then you have the IQ map and EBSD label indicates that the EBSD image is an overlay of an image quality. Okay, this is how most of the people uses or represent the EBSD images. So the low temperature nano twinning provides enhanced ductility. The engineering strain is more than 0.7 at failure. The stress of 1280 MPa. Okay, so this is one mechanism we are able to see under this, capturing the nano twinning. We will come to that discussion why nano twinning has to enhance the toughness. The cell structures, that is the dark patches, what is shown in this zoomed region, seen throughout the BSC image, especially on the inset, are due to the dislocation activity. Okay. So, the low magnification SEM images of surfaces containing fatigue cracks show many irregular shaped voids along the crack path, indicating that ductile fractures occurs by micro void coalescence. So, this is what you have to remember. So, when you have the irregular shapes of this void joined together, then you have this kind of a micro void coalescence will happen. So, this is what you can see, that there is a one void, there is another void, this another void, another void, they are all joined together, then it crack propagates like this. Signs of ductile fractures are present in both room temperature as well as 77 Kelvin fatigue cracks based upon the low magnification SEM. High magnification EBSD and BS images, however, reveal the important details and distinction between the room temperature and cryogenic deformation fracture behavior. So, this at least you should be able to appreciate what is room temperature deformation here. This is a cryo. So, you see a significant difference in the deformation behavior. Yeah, high density of nanotwins. So, the EBSD images of the room temperature crack tip show pronounced grain misorientation, which is shown in B, which are attributed to the glide of dislocations on 111 type crystal planes and may serve as the primary room temperature deformation mechanism. So, this is, so EBSD maps gives a orientation straight away, right. So, you will be able to see what kind of dislocation activity happens or where the deformation occurs and so on. We are able to capture by looking at this. So, most of the regions are zoomed here, you can see that it is close to 111 type misorientation. Several twins are also visible near the room temperature crack tip, which are identified as annealing twins because they are present throughout the bulk of the annealed sample. But in contrary to this observation, the immediate vicinity of the crack formed at 77 Kelvin, however, EBSD and BSE images show nanotwinning, closely spaced twins on the nanometer scale. Nanotwins appear in addition to the dislocation shell structures which are associated with the above mentioned dislocation glide. So, it is concluded that therefore, a nanotwinning provides an extra deformation mechanisms at cryogenic temperatures and is responsible for the enhanced ductility and exceptional toughness of the cobalt, chromium, iron, manganese, nickel high entropy alloy. So, now we have concluded by this observation or analysis, the nanotwinning provides an extra deformation mechanism. So, what do you mean by that? So, this is what you have to understand, right. So, we have observed all these things, now we have to interpret. So, what do you mean by extra deformation mechanism? So, that is what is that basic deformation mechanisms now? Huh? So, you have a basic deformation mechanism is slip, okay, that happens anyway for any material, whether irrespective of the temperature, whether room temperature or high temperature, it happens. So, in addition to that slip, then twinning is also another mechanism which happens at a very nanoscale level. So, that means if you look at in terms of energy absorption characteristic of any deformation process, a slip versus twinning, which is require more energy. This also you should look at it. Which requires more energy? Twinning. So, that means I have already slip happening, then I have an extra nanotwinning which absorbs lot more energy. So, that is related to your toughness. So, that is the idea. Okay. So, the fracture toughness study of this alloy demonstrates the value of integrated mechanical testing and the microscopy experiment plan. Of course, the tests were conducted in a compact tension specimen like what I showed you. Again, we have combined all this techniques, BSE and EBSD here, to just identify this orientation, especially wherever you have a deformation related study are required. It is wiser to look at EBSD, use EBSD, because it gives a orientation. You can identify the kind of slip direction, twin plane. We will be able to correlate with that. Okay. And then what is that stereo microscopy I talked about? So this is what you are seeing here. This is an SEM micrograph of a room temperature crack surface covered with dimples, lot of dimples you can see, which is an indication of ductile fracture mode. You are also seeing some of the zoomed surfaces. You can see all the dimples contains some particles inside. Okay. And these particles were determined to be chromium rich and manganese rich from the EDS analysis. So obviously you can see that. And you have this a 3-dimensional fracture surface was rendered by using SEM stereo image pairs. You can generate stereo image pairs in SEM software. Okay. The different morphologies of the fatigue pre-crack zone. So you have 3 different regions here. So 1, 2 and then 3. So the first zone is a pre-crack zone, and then second zone is a little darker, that is a stretch zone, and then finally the fracture, ductile fracture zone, you can say that. So this is this way of looking at this stereo image pairs also tells much more closely how the crack propagates, right? You will be able to identify the crack propagation path very closely. So that's the advantage of having a stereo microscopy. Okay, so this is the next case study of phase decomposition in aluminum, cobalt, chromium, copper, iron, nickel. High resolution TEM and an APT, these techniques are used to identify this phenomenon. Although high entropy alloys have a tendency to form solid solutions with simple crystal structures, detailed examinations of the microstructure sometimes reveal significant complexity. Okay. So the aluminum, cobalt, chromium, copper, iron, nickel high entropy alloy is an excellent example for this kind of microstructure. So what are the sample conditions? We are comparing the splat quenched versus conventional cast samples using high resolution electron microscopy and atom probe tomography. And XRD was also used to identify major phases. And then advanced sample preparation techniques, particularly splat quenching, which is produced cooling rates on the order of 106 Kelvin per second, play a key role in this study. Okay. It was shown that the quenched sample consisted of a single phase, imperfectly ordered solid solution, while the cast samples formed a complex multi-phase microstructures. We will see what are those. So we look at this XRD pattern as usual. We are comparing this as-cast and splat quenched high entropy alloy samples. The as-cast samples separate into 3 different phases: FCC1, FCC2 and BCC, while the splat quenched samples appear to be of a single phase. So you can see that splat quenched sample exhibiting a single phase, an as-cast sample has 3 different phases. The square one is BCC, the circle one is FCC1, the triangle is FCC2, which is quite good enough to have a complicated microstructure actually. So, this is a TEM images of this flat quenched single phase alloy, and this bright field image shows a polycrystalline microstructure, and what you see is again I am telling you this bright and dark contrast is because of the diffraction contrast, right, and a dark field image using 100 superlattice reflection reveals a domain like structures within the grains. Inset shows the SAD pattern. So, this pattern again I am telling you this is 100 is a fundamental reflection, and then you have a superlattice spots, and then one of the superlattice spot is being used to generate this image, which shows kind of white patches, that means domain in that matrix. Okay. The SAD pattern corresponds to an ordered BCC or B2 structure, and the dark field was produced by 100 superlattice. Okay. The spots on the dark field image are ultimately interpreted as imperfectly ordered B2 phase, right, consisting of a mixture of B2 and BCC domains within a coherent crystal structure. So, this is the result of that analysis, and further we use this APT techniques in the ASCAS sample to show the phase separated microstructure similar to the results of earlier study. However, the new details of the atomic level phase decomposition were obtained using APT. So, this is very important, right. So, in electron microscopy still we talk about relatively coarse information, not an atomic level information. In APT, you have an individual atoms are stripped from the specimen and specially prepared as a sharp tip. So, this is a sample being prepared as a sharp tip. This is an APT tip. It is done by focused ion beam milling microscope. This is again a special microscope for this. So, you have to make it very sharp, the tip, and then the atoms are evaporated from this tip one by one. So, the APT studies provided an atom maps within various microstructural features such as aluminum nickel enriched B2 ordered plates and chromium iron enriched BCC interpolates and copper rich plate precipitates. So, we are talking about three different type of segregation or phase decomposition, which is summarized here. So, what you see here is atom maps from APT study of the ASCAS aluminum, cobalt, chromium, copper, iron, nickel. The numbered regions correspond to aluminum nickel enriched region 1. So, this is, so aluminum is blue and the nickel is orange. So, you can see that aluminum nickel regions are shown here, and second region 2 is chromium iron rich region. So, you can see this violet region and then talk about iron, these are rich here. So, these two are rich in this region 2, and you have a copper rich plate precipitate in the region 3. So, you have a copper completely dominating in this region 3. So, you see we are talking about the length scale of very, very small nanometer scale. You have a phase decomposition which is not easily identifiable even in electron microscopy, but you have a three-dimensional information in this technique. So, by correlating the APT and high resolution microscopy results a very detailed picture of an extensive phase decomposition in a ASCAS aluminum, cobalt, chromium, copper, iron alloy has been emerged. The splat quenched sample had a single phase solid solution character. Of course, the single phase character was also supported by the XRD and the bright field TEM images. So, this is another characterization methods. Suppose if you want to look at the decomposition at atomic scale, and the moment you identify the phases having 2-3 crystal systems mixed, then it's better to select these kind of microstructure characterization techniques to get the full idea about the phase composition. So, this has been just summarized what we have just seen in the previous slide, and we can look at the same image in the high resolution TEM. Individual atom columns can be resolved, and the coherent lattice structure of the different phases can be strictly observed or directly observed. And for that, in a normal TEM, we need to use a technique called high resolution high angle angular dark field images. We can produce this. And then with these techniques, it was determined that the interfacial planes, the planes separating the BCC and B2 plates, have normals in 0, 0, 1 direction. So, the samples could be then tilted about 0, 0, 1 axis without significantly changing the projection of the interfaces. When the sample was tilted such that the electron beam direction was near 110, a pronounced contrast was found between B2 and BCC regions. So, why I am just bringing all these pointers, you can always look at the atomic level information in high resolution TEM, but then you need to know the orientation of this, whatever the interface you are interested. So, you have to orient that local region to that particular orientation. For example, we are saying that the interface between this BCC and B2 has normals in 1, 0, 0 direction. So, then that means if you want to look at that interface more clearly, you have to orient that phase clearly to this. That tilting facility is available in TEM. You can tilt them, and then so in particular, the spots in the B2 regions have alternating intensity, forming rows of above average and rows of below average intensities. So, this kind of images should be available from the head of imaging. So, when you say high angle annular dark field image, it is something similar to what you do in SEM. You are trying to collect the scattered intensity by a detector, right? Like you have a BSE detector, secondary electron detector. Here also you have a detector. It will collect all the scattered intensities. When you say high angle annular dark field, means you have an annular detector. It is an annular ring which will collect all the scattered signals. Then you will get this kind of images, atomic column informations. And then by looking at these scattered intensities, for example, because every atom will scatter differently depending upon the atomic number, right? So, suppose if I have multiple principal alloying elements, so each element will scatter differently. So, the element which scatters more will appear much brighter than the other elements. So, I can look at these atomic columns, whichever is brighter, then I will be able to relate with their corresponding atomic number. I can do that in this images. So, this is the image I was talking about. I think there is a mixing of the slides. So, what you are seeing here is a B2 structure. This is an HADAF image, and then you have the BCC phase is here, and then you have interface. So, your eyes need to get tuned to look at this. It will mislead you. Then you have to really focus. you can see that there is a bright line, all the bright spots, and then immediately after that there is a dull spot, and then again bright, and then again dull. So you have two different elements, atomic scattering factor is different, so accordingly they will appear like that. But if you look at this interface is like this, what you are seeing is what I was talking about, this orientation of this interface is 1, 0, 0, then it appears like this. Okay. So that's what I was telling. The electron beam is aligned along with 1, 1, 0 direction. The interface normally is along 0, 0, 1. So you have to tilt that. And the B2 phase has alternating intensities, and BCC phase has much more uniform atom column intensities. So you see that all the atom columns are having uniform intensity here, but here it is alternating, okay, because of the B2 phase. Okay. So the interface region is about 2 nanometer thick and has different intensity profile than the either BCC or B2 regions. Each region is associated with a particular composition structure. I'll go back to this. And we can also comment on the phase. So the atomic scale resolution and Z sensitivity of the Hadoff measurements were crucial factors in identifying the interface phase, which may play an important role in mechanical properties of high entropy alloys. Okay. So Hadoff technique is very useful and very important technique in identifying this. And if you look at these phase interfaces, nature of interfaces of similar alloys, again this Hadoff imaging and EDS mapping combination will be much more effective. And what is this you are seeing here? For example, this is EDS map. What is the difference you are seeing? What kind of information you will get by? What is that? Can you just identify what are the differences? It all looks similar in one go, but if you have a close look at it, you will have very interesting features to be identified. Look at this first, the Hadoff image before you look at the EDS maps. The Hadoff image has got some needle type of precipitates and some kind of interdendrites kind of a structure, right? That is how first we have to look at the Hadoff, and then look at the chemical map where they appear similar, where they appear different. For example, if you have nickel, aluminum, cobalt, all this images segregation appears same. Copper, chromium, iron, they are entirely opposite, isn't it? The segregation in these phases are opposite to what you are seeing here. Okay. So that means there is a selection of elements in the phase interfaces. Okay. So how do we understand that? So the phase separation in the aluminum, cobalt, chromium, copper, iron system has been thoroughly studied. How this Hadoff study in the nanoscale microstructural features and even atomic level details interface between B2 and BCC phases in this alloy. So we have combined this Hadoff and EDS, and then we looked at the elements like nickel, aluminum, cobalt, and small amounts of iron, copper tend to partition in one of the plate-like phases. So we are seeing nickel, aluminum, cobalt corresponds to plate-like phases. Of course, they have a small amount of iron and copper. So nickel, aluminum, cobalt. So, nickel, aluminum, cobalt. These are the phases, plate-like phases, and they have very small dissolution of iron and copper. Similarly, we have chromium, iron and small amounts of cobalt tend to partition to the other two plate-like phases. So, that is what we are seeing here in this section. Okay. In addition, they have a copper-rich plates also seen in this particular. This I have already described about this high resolution images. Now, we will go to the another case study, very interesting, chemical disorder verified using anomalous X-ray diffraction and neutron scattering. This is quite new, not the conventional characterization techniques what normally we do, right. The question is, why do we do this? Chemical disorder verified using anomalous X-ray diffraction. We know that ordered structures have been detected in many high entropy alloys such as aluminum, cobalt, chromium, copper, iron, nickel, based on the appearance of superstructures reflections in the XRD. The detection of XRD superstructure reflection, however, is possible only when there is a sufficient difference in X-ray scattering factors, F, structure factor or atomic scattering factor of elements in the ordered high entropy phase. The same requirement applies to neutron diffraction. So, where the neutron scattering lengths B among the elements must be sufficiently different to be sensitive to ordered versus disordered distribution. So, it is important to note that F and B follow very different trends across the periodic table, which is a great motivation for conducting complementary X-ray and neutron scattering studies. So, you combine both XRD and neutron scattering because neutron scattering follows a different trend in a periodic table. So, you have in a conventional XRD using copper K alpha radiation, for example, there are small differences in F, that is atomic scattering factor for elements with the similar atomic numbers. So, consequently, conventional XRD cannot distinguish between ordered and disordered distribution of the transition metals at least, right. So, aluminum, however, has a slightly lower atomic scattering factor than the 3D transition metal. Therefore, B2 order has been readily detected in this aluminum, cobalt, chromium, copper, iron, nickel family, even using conventional XRD. Despite the detection of B2 order in aluminum containing high entropy alloys, a detailed knowledge of the atomic distribution is not feasible based on the conventional XRD data. So, people use something called anomalous X-ray diffraction. It may be used to create scattering contrast needed to detect ordering in high entropy alloys. What is this anomalous X-ray diffraction? Lucas et al. Applied anomalous XRD and neutron scattering to demonstrate that cobalt, chromium, iron, nickel alloy lacks the long range chemical order. So, this is the target. How do you prove that particular alloy do not exhibit the long range chemical order? That is the focus or objective here. So, if you take the conventional XRD with the copper K alpha, you have atomic scattering factor of iron, nickel, chromium, cobalt, and the structure factors are similar. So, no superlattice reflections will be detected even if the alloy is ordered. So, this is quite tricky. So, what is involved in anomalous XRD? In using anomalous XRD, the incident photon energies are tuned to K edge of the selected element. So, this is the trick, significantly reducing its scattering factor. Then the sensitivity to chemical ordering is thus greatly enhanced. So, Lucas et al. Introduced the ordered iron nickel compound FeNi3 as a control sample in their study of cobalt, chromium, iron, nickel alloy to verify that their measurement was sensitive to the chemical order. So, it is a kind of a reference sample to check whether what kind of order exists in this cobalt, chromium, iron, nickel alloy. So, when the cobalt, chromium, iron, nickel alloy showed no signs of order in anomalous XRD measurement, it made a convincing case that the alloy indeed lacked the long range chemical order. So, that is one kind of idea. So, you can have three type of solid solution which you know already. So, you can have a random solid solution where all the atom can occupy the normal lattice, or you can have an L1-2 ordered structures where the gray atoms represent nickel atoms for FeNi3, or a random mixture of chromium, cobalt and nickel atoms for iron. Instead of iron Ni3, you can have iron, cobalt, chromium Ni3, any one of this can form, or you can have a fully ordered cobalt, chromium, iron, nickel alloy. So, all three possibilities are there. So, what is that basis of anomalous XRD? So, you have the scattering factor versus photon energy. I said this photon energy is tuned to the k edge of each element, right? That is the basis. So, the real part of the scattering factor as a function of photon energy shows the sharp dips. So, you can see nice sharp dips of all these elements. The dashed vertical lines are the energies used for anomalous XRD experiments on the cobalt, chromium, iron, nickel high entropy alloy. And how does this compare with the result? So, anomalous X-ray diffraction patterns comparing iron nickel, which has a strong tendency to order, with the equimolar cobalt, chromium, iron, nickel, which shows no tendency to order. So, you can clearly see that this is a reference material FeNi3 annealed, which shows an ordered phase here, and you can look at iron, cobalt, chromium, nickel here, you do not have any clear signal of ordering. One information about anomalous X-ray. How about neutron scattering? In the case of neutron scattering, the scattering lengths B for iron, nickel, cobalt and chromium will replace the scattering factors F. Okay. So, these neutron scattering lengths have a significant variation, what you can see in the table. Definitely when you have this kind of a variation, it will provide a modest sensitivity to ordering if you have this. Okay. So, the study including this alloy, both neutron diffraction and XRD measurements with consistent results, that shows the alloy lacks a long range order. So, this is one little sophisticated techniques which is required when you have a complex high entropy alloy systems. I think I have one interesting observation. It is in situ neutron diffraction study of the deformation behavior of cobalt, chromium, iron, nickel high entropy alloy. So, why do we do in situ deformation study? That is first thing. We say that in situ neutron diffraction study. Most of this kind of a sophisticated analytical techniques or tools, they are available as in the national center. It is not easy to set it up in every university or any research labs. So, you have a neutron diffraction facilities in India, you have a DAE labs, all the DAE labs will have, but if you internationally, lot of labs are accessible to everybody, all academic people can go and do these experiments. And looking at this kind of a complex high entropy alloy deformation study, this kind of neutron diffraction will shed a light in much more detail as compared to the conventional deformation or in situ study in the normal electron microscopy or X-ray diffraction. So, what you are seeing is a diffraction geometry for measuring lattice strains due to the applied tensile loads are shown here. Okay, this is a neutron beam and this is a tensile force is applied in this direction, and you have a detector. 2 detectors are placed in this, and then the actual setup is shown here. You have the sample is a heating coil, and you can see the sample is heated, and these are the loading frames. The schematic diagram showing a sample oriented at 45° to the incident neutron beam and 2 detectors at 90° to the beam direction. The scattering vectors of the diffracted beam collected on a north and south detectors are transverse and parallel to the sample axis. So, this is important. Thus, the transverse and the parallel lattice strains are detected separately. So, our aim is to understand the deformation behavior. In deformation, what do you measure? You measure the strain, right? So, what is the basis of this? So, the basis is given here. The applied stress leads to changes in the lattice constants, elastic lattice strains, which are determined by precisely tracking the position of the Bragg reflection during loading. The lattice strain epsilon HKL, which may be strongly dependent on the crystal grain orientation HKL, is calculated by this relation. Epsilon HKL is equal to DHKL minus DHKL-O divided by DHKL-O, where DHKL is the d-spacing for a given HKL reflection at a load, and DHKL0 is the value at 0 load. Okay. In addition to the peak positions, the relative intensities may change during the loading, which often indicates the changes in texture caused by plastic deformation. This is important. Another important aspect of the in situ neutron diffraction study is the simultaneous measurement of macroscopic strain determined by the load frame displacement or strain gauges on the sample. Ultimately, the combined observations of the lattice strain, macroscopic strain and the texture evolution may lead to a detailed understanding of high entropy alloy deformation behavior. So, this is the background for this. We are interested in measuring the lattice strain and macroscopic strain. Okay. So, the cobalt, chromium, iron, nickel high entropy alloy consists mostly of a single phase, that is FCC. Therefore, it is interesting comparison to the conventional FCC metals. So, we can compare these two metals because it is same crystal structure. One important comparison concerns the elastic lattice strain behavior, which in conventional FCC metals is anisotropic. This I think you know. In a simple FCC crystal system, the deformation is anisotropic with a soft 100 direction attributed to the low atomic packing density and the large interplanar distance in 100 plane. That is why it is like that. In FCC cobalt, chromium, iron, nickel alloy, however, the atomic separation and interactions vary from atom to atom. So, this is a difference. We have a conventional FCC system which we know what happens in 100 plane and 100 direction, but in this complex alloys, the interaction from the atom to atom differ, so that will have a different effect. So, this study shed some light on the impact of these local fluctuations on the deformation behavior of the cobalt, chromium, iron, nickel alloy. So, what do we see here? We have diffraction pattern of cobalt, chromium, iron, nickel confirms that alloy is mostly a single phase, and then B is a tensile stress strain curve, shows the some features as a conventional FCC metals, such as low yield strength around 200 MPa and then large tensile plasticity. You can see that. Considerable work hardening. So, you can see that it is keep on increasing till about 40%, 45%. The inset shows the SEM image of the lateral fracture surface with the typical FCC features such as numerous slip bands. Okay. So, you can see a kind of very interesting slip bands, very high density narrow slip bands. What does neutron diffraction does? The neutron diffraction pattern verified FCC structure, and the tensile stress strain showed the macroscopic deformation behavior of cobalt chromium iron nickel alloy is similar to that of FCC metals. So, there is no difference in this case, even though this is a complex alloy, there is no significant difference. In particular, this cobalt chromium iron nickel alloy has a low yield strength, large tensile plasticity, and a work hardening coefficient of 0.47, which is similar to that of FCC copper, which is quite interesting, right? In spite of all this complexity, it behaves like a copper. So, what you are seeing here is the lattice strain evolution shows a strong anisotropic strain response typical of an FCC structure. So, this is a tensile stress versus lattice strain. And what is interesting here? What is interesting here? This is a true stress, this is a lattice strain. What is interesting here? The lattice strain is significantly more in 200, right? It is very different from the rest of the orientations. So, the lattice strains and the deformation induced changes in the peak intensities indicate that the cobalt chromium iron nickel alloys deformation behavior is similar to that of conventional FCC metals. Based on the despacing shifts, the 200 grains have significantly larger elastic strain than the other orientations. Okay. The other orientations are like 111, 220, 311 and 331, which is expected in FCC metal. This is what you said, right? This is what you said, which is expected in FCC metals. So, maybe because of the shift, large shift. The another point is the ratio of the elastic stiffness, that is the slope of stress and lattice strain curves in 111 and 100 directions was found to be 1.98, close to pure nickel. So, this plot is again quite interesting. The intensity change significantly happens after tensile stress of 200 MPa, and that is particularly more for 200 and 220. But other orientations, they are all same. The deformation induced intensity changes are similar to those observed in FCC metals and conventional FCC alloys, in which the textured structure forms during tensile elongation, right? So, the in situ neutron diffraction technique during loading provides macroscopic and microscopic information about deformation behavior and mechanisms in high entropy alloys. The technique rigorously verified that the room temperature deformation behavior of cobalt chromium iron nickel alloy was similar to that of conventional alloys. Of course, this similarity does not necessarily hold for all high entropy alloys, right, and for different temperature ranges. So, this is just one coincidence that it appears similar, but for detecting the deformation behavior very closely, you need to have these kind of neutron diffraction experiments, then which can capture the deformations much more closely. I think I will stop here, then we will continue in the next class.